Everybody. Thank you for joining us today, and special thanks to Jefferson Lab for rescheduling this tour. So welcome to the remote experience for young engineers and scientists program known as REYES. My name is Rachel White, and I am a member of the REYES planning team. I will serve as your host for today's lecture, Tour of Jefferson Lab Experimental Halls. In this virtual tour through halls A and D of the experimental facilities at Jefferson Lab in Newport News, Virginia, we will introduce a general audience to the techniques and apparatus that are used to do cutting-edge research into the structure and dynamics of strongly interacting matter. Throughout this webcast, you may submit questions through the Q&A box of a Zoom screen. Following this tour, we will answer as many questions as time allows. Today's session will be hosted by Uran Tadabali and Mark Dalton, staff of Jefferson Lab National Particle Accelerator. Please join me in welcoming Jefferson Lab to REYES.
Hello, everybody. Can you hear me? See me okay?
Yep, I can see and hear you. Thank you.
So welcome to Jefferson Lab. First, as Rachel introduced me, I'm a staff scientist in Hall A and C, and I'm involved in a bunch of experiments. My responsibility is to work on polarized targets, and my current project is to work on developing polarized helium-3 for one of the experiments that's currently ongoing in Hall. We study nucleon form factors, and next it will be another experiment to study something else. And so I wanted to give you a very quick presentation on what to expect from this virtual tour, and hopefully you're able to see my screen, and then walk with you and show you some of the equipment that we use in the experiment. But first, Mark and I welcome you to this tour, and thank you so much to the REYES team, and in particular our colleague and friend Raul, and also thanks to Georgina, Jeff, and Rachel for organizing this and for helping create a platform so we can communicate with you all. So some of the smallest things that you may think of are, ants, sand, and screws, and mustard seeds, and dust, and all these things. But there is a common thread to some of these things. If you go a little further deeper, then you may find things like DNA and RNA and elements, and you enter the world of atoms and the world of chemistry. It's also extremely fascinating. But that's another layer of reality, if I may, that we have several different rules to try and explain the various different phenomena that actually happen that govern the universe from this level. We go another level inside, then we find protons and neutrons that make up the atomic nuclei. Blue ones are neutrons, red ones are protons, and it's just a sample. In reality, they're not these kind of colors. They're just these particles that are composite particles, which there's more deeper structure to it. And if we go inside the atomic nucleus and zoom in on these particles, then there are these neutrons, which are up quarks and down quarks. And there's also a lot of stuff that happens inside these, which is that these up quarks and down quarks are communicating with each other in the form of exchanging gluons. And these gluons are the force carriers, just like how the proton is the force carrier for the electromagnetic force. Similarly, the gluon is the carrier of the strong nuclear force. And then all these are happening inside the nucleus. They're happening right now. It's happening right now in every atom that we know. These forces are being exchanged, and the atom is kept together. Nucleus is kept together, and it's an unavoidable reality. But what would make it interesting is if we get some insight into how this actually happens, and what can we do to learn more about this fundamental force called strong force. And so the smallest of the small, which are invisible to the eyes, define the matter that we're made up of. And for me personally, it's an honor, pleasure, gift, and a beautiful journey to be able to understand and play with the building blocks and dance with nature. So, place that we are going to give you a tour of is Jefferson Lab. Check out this website to get more information on various different experiments that have been conducted the last 30 years. So a lot has been done in Jefferson Lab. I'm here to only talk about just one experiment in the grand scheme of several different physics topics that we can explore here. So there are 4 different experimental halls: Hall A, Hall B, Hall C, Hall D. And I will show you Hall A, and Mark will show you Hall D. And each of these experimental halls is designed to study something really fundamental and different and interesting. So at someday, hopefully, you are able to come in person and join us at Jefferson Lab. But for now, join me on this tour. Let me stop my screen share and hopefully you can see my video. Okay. Let's see. Okay. Are you able to okay, so maybe I can switch to this device as the main device and show you the experimental model. Okay. Okay, so hopefully you're able to see the device that shows not me, but the experimental hall itself. Let's see. Okay, so Rachel, could you confirm that you're able to hear me and can see the video?
Yes, we can see and hear you. Just make sure you speak loudly enough, given that your speaker's turned away from you. But it looks good. Thank you.
Okay, hold on. Okay, is it better?
Yes.
Okay, so let me show you the experimental hall. And we're walking towards one of the experimental setups here. So first, that's the climbing up the stairs to go see the target region, and it's currently blocked off because there's target work that needs to be done in there, and then need approval to go in there. It's blocked off, but you can see the beam line. This beam line here, that's where the electron beam comes in, and the electron beam gets generated, and machine control center, or the MCC folks, are the ones who deliver the beam to us, and it goes through a series of linacs and superconducting cavities and reaches us here. And up till here is what Jefferson Lab is able to provide for conducting the experiments. Various different universities and labs all around the world, right, come here with the common goal to set up their experimental equipment downstream of this and study their physics topic that they of their choice. Right. So the electron beam comes in here. Target is inside this enclosure. You know, we are not able to open the enclosure at this point, but you can see that once the electron beam comes in and scatters to the target, there are 2 particles, or the physics that we're interested in is an elastic process. That means the electron scatters off of this nucleon, and the nucleon gets scattered and moves towards in this direction towards the towards that detector subsystem. So what you see here in front of you is a giant magnet, right? Can you imagine a magnet being that big? It is actually 20 tons. And of course, you have to run current through it to make it active, but it's not currently running. But this is the magnet that you're looking at, the super big bang spectrometer magnet, the SBS magnet, and it's that's huge. There's no way you can put this magnet on your refrigerator. Probably put the refrigerator on this magnet, but it's huge. Then the nucleon gets scattered. Then there are a bunch of detectors here called the GEMS, or gas electron multiplier technology, that use this technology that kind of reconstruct the trajectory of the scattered nucleon. Then they come and traverse the path, and they hit this calorimeter or hadron calorimeter. It's actually 20 feet high. It's really, really big. You can't really tell from the computer screen, but you can fit two of people of my size on top of each other to reach the top. It's a huge detector, and they look at the stairs to go up to there, and then it's just the electronic. Then from there on, we have a lot of the electrons that don't interact with the target because the nucleus is so empty, right? The electrons which are on the outer parts, and then or the outer shells, or the periphery of the nucleon, and then there's nucleon, which is, as Rutherford has pointed out to us, that is focused into a very, very small volume. So most of the electron beam just goes through dot scattering. So you have to find a place which is safe to deposit these the unscattered electron beam. That's what it's called, a beam dump. You use various different cooling technologies to kind of redistribute the heat that is generated when this electron beam gets deposited at this place. Then see, this is the heat dump. And then this is the other part of the spectrometer, because it has two arms. That's the other part where the electron gets detected. Remember, the first arm was where the nucleon got detected, and the second part is where the electron got detected. And that's another magnet where these two magnets, as you can see, have been clamped to the ground. So when you run current through it, it generates a field of about a few Tesla that is used to redirect the trajectory of the electron into the detector stack. And there are a bunch of detectors. There are GEMS, there's a photoscope, there's a Cherenkov, then there's a calorimeter, and all these electronics are used to trigger on a particular type of event that we're interested in. So each of these detectors has a unique purpose. Magnet, of course, is to bend the charged particles and separate it from the neutral ones and redirect it into a stack of detectors which are placed strategically. The GEMS are basically used for track reconstruction. Wherever this charged particle goes, it leaves ionization trail, so you can reconstruct the track from these various different points, like connecting the dots. Then you have timing photoscopes, which are used for triggering purposes. Basically, if a particle passes through, then signal from it traverses to the data acquisition system at a faster speed compared to the other detectors. So you can tell your data acquisition system that, hey, there's an event, it's really interesting that just passed through, you might want to wait for it, and then records it based on that particular time window that is set based on how long it takes for the signal to travel from that detector stack to equipment. And there's a calorimeter, which is used for determining, or there's a Cherenkov, which is used for particle ID, which means each of these charged particles, depends on its mass, generates different amount of Cherenkov radiation that gets detected by the PMPs. And because each of these give out different types of radiation, which are characteristic of the type of particle that's used for PID purposes, particle identification purposes. finally, there's a calorimeter where this electron comes in and interacts with the calorimeter and deposits energy. So you have energy, reconstructed points from which you can get the momentum, then you can get the charge particle type. So you have all this information to reconstruct kinematics. From there on, go back to the target region, extrapolate this, go back to the target region, and get your physics out of it. So that's the main goal of this, is you place the detectors strategically at different angles relative to target region. You can rotate them independently, or each of them can rotate independently also, or you can rotate them together. But the idea is that you strategically place these detectors so as to capture the physics of interest. And such experiment, but the history of Hawley, many such experiments that have been conducted, and hopefully I've given you a very gist of what goes on. We try to study the smallest things and strongest things, try to connect these three together. Okay, thank you very much. That was Arun live from Hawley. So maybe I introduce Mark at this point. Mark, are you ready?
Yeah, I'm ready. I'm ready to go.
Awesome. So, Rachel, maybe I introduce Mark here. So Mark is a very dear friend and colleague who also works at Jefferson Lab, and he is a staff scientist in Hall D. He's received his PhD from University of Witwatersrand, Johannesburg, South Africa, and he is currently a staff in Hall D. He's worked on very different types of physics throughout his career and brings in a very broad experience to Jefferson Lab. He's mentored many PhD students, grad students, undergrads, and is a pleasure to work with. So, Mark, please take away.
Thank you, Arun, for very kind introduction. So, and also I appreciate your introduction to the topics that we're talking about here today. So, as Arun mentioned, the protons and the neutrons that make up all the matter around us, they're composed of quarks and gluons. So the quarks, the up and down quarks that we find in a proton and a neutron, they're bound together with gluons. And this is all described by a theory called quantum chromodynamics. But it turns out that the proton and the neutron, they're not the only arrangements of quarks that you can get. Actually, there's really hundreds of arrangements of quarks that exist. You get the up and the down quark, but you also get the charm, the strain, the top and the bottom quark. You get different arrangements of quark spins. You can give them radial excitation. So it turns out that there's just a huge number of ways to arrange the quarks. And what we do here in Hall D primarily is study the ways of arranging those quarks, and we call this spectroscopy. So if you have a quark and an antiquark pair that are bound together, this is what we call a meson. And we know of a huge number of mesons, and we have models that explain the way they interact, the way they behave, and how they're composed. But we are in our field constantly finding new particles with different arrangements of quarks that we didn't expect. So for a time, we thought that quarks came in 3 quarks states like protons and neutrons, or a quark-antiquark pair like a meson. But now 4 quark states, 5 quark states are being discovered pretty regularly. And here in Hall D, we're looking for a meson, which we call a hybrid meson, where it's probably going to be made out of 2 quarks, but there's some non-trivial gluonic degree of freedom that's contributing to the quantum number. So you can think of it maybe as 2 quarks and a constituent gluon. And there's quite a lot of evidence to suggest that something called the pi1 meson is a hybrid meson and has already been detected. And we're trying to find support the evidence for that particle being discovered, and also find other ones. And by mapping out all the possible arrangements of the quarks in various states, we can get some kind of understanding into the underlying dynamics. So that's what all of this apparatus that you see behind me is for. So we're a little bit different from the Hall A setup. In fact, from the Hall A, B, and C in Hall D, because instead of using the electron beam directly, we have a real photon beam. So you won't see it in this hall, but about 80 meters upstream of us, we create a photon beam by putting an electron beam through a very thin diamond radiator, about 50 microns thick. It's a single crystal that's 50 microns thick. And when the beam goes through this matter, it produces radiation, photon. And by carefully orienting the crystal axis with the direction of the electron beam, we produce a coherent interaction that gives us a peak of high energy photons at 9 GeV. So that's each photon has the same amount of energy as 9 protons have mass. So it's really a lot of energy. And then that beam comes into the hall, and we use that beam here to try and create the hybrid mesons that we're interested in. So if you follow me, I'm going to take you up to the target region, which is where the beam goes and interacts with the matter, and then we're going to try and understand what comes out of it. So if we were to create a hybrid meson, we would be creating something that doesn't live very long, something that decays very quickly and might decay to a lot of particles. A hybrid meson might itself decay to 3 particles, 2 or 3, and each one of those particles that it decays into might then decay again into another 2 or 3 particles. We might end up with between 6 and 10 different particles in the final state. So we need a detector that's going to detect a lot of particles at the same time. And so that's what you see behind me over here. This is the Gluex spectrometer, and it's all built around this large superconducting solenoid. This big red cylinder that you see is a superconducting solenoid magnet with a field of about 2 Tesla. So it's like a big MRI machine, but it's bigger than the one you would find in the hospital. You could, if you were, crouched down, you could actually walk right through this thing. And it's very long as well, 4 meters long. So it's significantly larger than something you would find at a hospital, but it's about the same idea. So the photons that we create in our hall that I described already, they're coming from that direction to my right. They're following this beam line, and then they're arriving here at our target. So, excuse me. A physics experiment needs 3 basic ingredients. A scattering experiment, it needs a beam, it needs a target, and it needs detectors. So I've described the beam. This is the target, and the apparatus behind it is all part of it. The target is liquid hydrogen. The reason we use hydrogen is because it's a very simple target. It's just a single proton. We're interested in studying the beam rather than the target. The beam comes in, exchanges some particles with the target, and then becomes the hybrid meson that we're interested in. So for that reason, we choose the simplest target we can really lay our hands on. We have all this apparatus to liquefy it into a liquid, and then the liquid is pumped into the chamber here, about 30 centimeters long. And the reason we use the liquid is because it just increases the density of the target material, and that allows us to get more scattering. The more scattering, the more rare processes that we can study. And then, of course, we need detectors. So I'm going to talk about 4 different kinds of detectors today. We have timing detectors, tracking detectors, energy detectors or calorimeters, and particle ID detectors. So here, immediately surrounding the target, so you can't see the target itself, and you can't really see the detectors, but we have what we call the start counter. So these are timing detectors. They're thin, scintillating detectors. When a particle travels through, they produce a large amount of light. That light travels to a detector, which detects it in the end. And because the signal is fast and it rises rapidly, we can use it as a good way to start the clock on the whole measurement. So as soon as the particle travels through the start counter, we're essentially starting the clock. Then when we actually run the experiment, this target part, which is on rails, it can be slid into the magnet, and there's a hole in the center of the magnet where the target itself goes. And then immediately surrounding the target is the central drift chamber over here. And what you can't really see the drift chamber itself. What you see here is electronics related to the drift chamber, but the drift chamber is made out of many straws, and each straw is filled with gas. And there's a wire in the middle of the straw, and the straw itself is conducting. So we create an electric field between the wire and the straw. When the charged particle travels through the straw, it ionizes the gas, and that gas is able to then drift under the field between the two wires, and it's detected on the wire. By measuring the time difference from when the start counter says start to when the drifting ions arrive at the wire, then we can determine how far away the particle was from the wire. We have a lot of straws here, so we get a lot of different measurements of the position of the particle as it travels through this device. Because of our very strong magnetic field here, any charged particle that's traveling in this region is going to have a curved path, and that curvature of the path is proportional to the momentum of the particle. So we're mapping out points, many points along the trajectory of this particle. We can put a line to it. Based on the known field of the magnet, we determine what its momentum is. So that explains how we get the momentum of a charged particle. But we also have neutral particles, like we might have a photon. Now we need to measure the energy of a photon. For that, we have a different device. The photon is not going to ionize the gas. A photon is just going to travel through without interacting. So surrounding the drift chamber, you can't really see it, but all these wires and tubes are going to our calorimeter, which we call the barrel calorimeter. It's in the shape of a big cylinder. When the photon interacts with the barrel calorimeter, it's constructed of lead and scintillating fibers. It will deposit all of its energy very quickly and create a big shower of particles. You know, the photon produces an electron-positron pair. Each one of those produces some photons, and then those photons produce electron-positron pairs. And very quickly, one particle becomes an uncountable number of particles, and they deposit all their energy, and you get light. And that light travels to both ends of the calorimeter. We detect it. We can measure how much energy was deposited by measuring how much light there was. Okay. Okay, we sometimes get some PA system announcements based on the safety of the stream, so you have to listen to those. So the particles, the photons have been detected in our barrel calorimeter, and charged particles have been detected in the drift chamber, and we measured the timing start of the interaction. But the particles, the photons that are our beam, arrive here with a lot of momentum. So some of the stuff is coming out sideways, but most of the stuff is really going in the forward direction because we have a lot of momentum. So now we're going to walk downstairs and take a look in the forward direction and see what detectors we use there. Why don't we go back the way we came? Okay, so here we are in the forward direction. And if you look up over there, you can see the bore of the magnet, and you can see some detectors. We have another drift chamber, which we call the forward drift chamber, and that is of a somewhat different design to the central drift chamber, but it has basically the same principle, where the particles ionize the gas, and then the ionization drifts to a wire, and we can determine the position based on some timing and the location of the wire. Then the next thing we have here is what we call the DIRC detector, which is a Cherenkov detector like Arun was describing earlier, and the main intention of the Cherenkov detector is to help us determine what the particle was. So we've measured times, and we've measured positions, and we've measured trajectories, we've measured momentum, but we don't really know necessarily whether this is an electron, is it a pion, is it a kaon, is it a proton? it could be one of many different kinds of particles. So we're relying on the Cherenkov interaction here. When a particle travels through a material faster than the speed of light in that material, then it produces Cherenkov radiation. So this is quartz bars. Quartz has a refractive index of about 1 to 5 or something like that. So speed of light is only, about 60 to 70% of that in a vacuum when it travels through the quartz. So a particle could be traveling faster than the speed of light in the quartz, and then it produces this cone. The cone will bounce around in the quartz, and then eventually it will arrive at this optical box, which we use to create an image of that cone on a focal plane. And so essentially we get these rings, and by looking at the radius of the ring, we can tell something about the velocity of the particle. That's the basic principle. Then right now, we're a little bit lucky because you get to see the upgrading of a detector that we're doing right now in Hall D. So this is the forward calorimeter. It's the last detector that particles are going to see. And so any photons or particles that come in the forward direction are going to eventually hit this calorimeter. So it's being upgraded. The central part is being replaced. This whole thing used to be made out of lead glass, and it's being replaced with lead tungstate, which is denser, produces more light, so the detectors can be smaller, and so we can have better position resolution and better energy resolution. So we're currently reconstructing this, and we're about halfway through. And in reconstructing it, of course, we need to have a place to store all the components. So I'll give you an example of one of the things that we might install. Think about a little bit. This is a module of lead glass. It's heavy because it contains quite a lot of lead in it. You can see that it's clear. A particle that comes along is going to deposit its energy in the glass, and then the light that is produced will travel to the end and be detected by the detectors at the end. So this is electronics and the photomultiplier tube, which is the detector for the device. So that's a fun project that we're working on here in Hall D, and it should be ready in the new year. So I think that's about it for me. Why don't we go back to the computer and we can see whether there are any questions.
Thank you so much. I think that was a great tour. Not everyone gets to go down there and see the detectors. So if you have any questions, you can feel free to put them in the Q&A box. I can kind of start with saying, or just ask you guys, we sort of rushed through the beginning of this. Do you guys want to kind of give us some details of your specific roles at JLab and kind of why you were attracted to work there? Anyone can start.
Well, I was limited. Sorry, I was going to say I'll go first. For alphabetically, my name comes first. So I worked at Fermilab for about 8 years. It's another Department of Energy lab where I did my PhD thesis. And my wife is from Virginia, and I wasn't married back then. But basically, she said that there's this great place in Virginia that I have to come and check out. And I said, there's a great place in Chicago, Fermilab, that she has to come and check out. It turned out that I ended up moving here. She won. Jokes apart, I think this is a great place to do some fundamental science. I've always wanted to be on the frontier of action. And if there's something happening, I wanted to see it with my own eyes and use my own hands to work on something that I could see like it being directly impactful. And Jefferson Lab was such a place where I was very quickly brought in on many hardware projects. And I liked working on all these projects, and there's been more of it. And then last year I got hired as staff to work on more of it. So I think it was just a gradual process for me. It was not like I woke up one day and I said, this is what I want to do, but it was like going more and more and deeper into asking questions eventually led me to studying what the nucleon is made up of, and exploring or going to a place which pursued those fundamental questions that brought people together, which are like more like and that and the just wanting to explore things.
Great. Mark, how about you?
So as a young man, I was always interested in science and mathematics and kind of how the world worked. And my uncle is a physicist, so he would always tell me about how much fun he had doing that. So I ended up studying it at university, and I just, kind of a bit like Arun, I didn't know immediately that I wanted to be a physicist, but I ended up doing a PhD. And so if you want to be a physicist, you're going to have to do a PhD. That's kind of a minimum requirement, basically. Then after I'd finished my PhD, I looked around for fun projects to work on, and I found someone at the University of Virginia who was doing what I thought sounded like a really fun project, working on parity violation and electron scattering. So I joined him. For 5 years, we worked together, and I really enjoyed that a lot. And, I was pretty sure that I wanted to be a physicist, but it's a little tricky to find an opportunity to be a physicist. It's a kind of competitive environment. So I was applying for various positions in the US, in England, in South Africa. And then I got this job at Jefferson Lab in Haldi, and I'm very happy to be here working on that. So I have with me, so he's been helping me today, Malte Albrecht, who's another staff member here in Haldi, and maybe he can give you his perspective as well.
Sure. Yeah. Yeah. Like Mark said, my name is Malte. So I'm also, like Mark, a staff scientist here for Haldi. And for me, it was my high school teacher, my high school physics teacher, actually. He made us do a summer project to work on a topic or work out something that we didn't cover in the school year. And I chose a nearby university. They had a super small accelerator in the basement. That's in Germany. And I went there, and there was a guy running this thing, and he showed me everything, and I was super fascinated. And ever since then, I've been hooked, basically. And then made my way, did a PhD also in Germany, and then came to the US for a postdoc, and now working for the lab as a staff scientist.
Great. So there is a question in the chat, and it goes a little bit with Mark. You said, you kind of need to get your PhD in physics, but there are several different areas of science and engineering and IT that work at Jefferson Lab to make it operate. So this question says, what educational qualifications are required for working in this lab?
So I made the mistake of assuming that they were talking about as a physicist. So as a physicist, you're going to have to do a PhD, but if you work as an engineer, and there are actually quite a lot of fun opportunities for engineers here, for technical people that work with electronics or that kind of thing, then you would have, I'm not entirely sure exactly what you need. You probably need a normal engineering degree and then some experience. But for physics, you're going to need a PhD for sure.
Mm-hmm. So the next question says, does JLab hire theoretical physicists? If I was to answer that, I'd say yes. There's the theoretical nuclear physicists, right? So do you guys want to kind of expand on that?
Yes. So we have a theoretical division. We don't have a lot of physicists that work for the lab specifically. We maybe just a handful. We have many theoretical physicists that are sort of employed both by the lab and by universities in a bridge position or a joint position, something like that. And then we have many younger physicists doing postdoctoral studies who are employed either by the lab or partly by the lab and partly by universities. So the theory group is quite large. They have a whole wing of our building, but they don't employ, by the lab, that many people in a permanent capacity.
And just to add to that, for us as experimentalists, we depend critically also on the input from our theory colleagues. So of course we have to run the experiments and build the experiments, which they have basically not much to do with. But once we get the physics data, or even before we get the physics data, the communication with our nuclear theory colleagues is really vital.
Did you want to add anything, or we're good?
Oh, I agree.
Yeah, okay. Okay. So for me, I was actually a student at ODU in physics, and I did a undergraduate research project there. It was I think they called it SULI back then, and I actually got to spend 6 weeks at the lab, and I worked with a Hall A nuclear physicist, and it was just a really great experience. Do you guys work with undergrads or even high school students? Is that something that the lab still does?
Yeah. I mean, just 2 weeks ago, I finished mentoring 4 high school students from various different schools all over Virginia. I think they were in the SCDR program. There's also like governor school mentoring program. There are 4 or 5 mentoring programs like that for undergrad and graduate. Last year, I mentored 4 undergrads, and I've been working with a lot of grads. I think that's really active part of inspiring the next generation is the work with these people, and hopefully someone from the audience will get inspired today and come and work in Hall A. But that's how I ended up with, because I had a very caring and compassionate mentor who, when I was an undergrad, said to me that I should not be afraid of making mistakes, and I should explore and make the experiment in physics kind of like an awareness kind of thing. That you have to be really observant as to what's happening in front of you, make changes, try to study with your mind as to what's going on, make the equipment work, and then interpret the data that comes out of it. And those kind of really mentoring experiences and moments that I had some great mentors in my life. The reason why I am here today. Jefferson Lab does a lot of programs. They are crucial for its fundamental.
Right. Yeah, that's all. There's a large number during the summers, particularly, of undergraduate students that come to the lab. So if there are any undergraduates out there that are interested, you should look into the SULI or REU programs, and they will fully fund your stay here, accommodation, a stipend, and travel and all that you need. So yeah, we encourage people to come along and work with us. Malte and I have been working with a couple of undergraduate students who we found very helpful building this big calorimeter that I was showing you today. And so
Excellent. So another question is, how does your job involve experiments daily based on the theories that I guess are developed? So it goes back to that theoretical physicist, and then what does the data kind of show you?
So I think this question is a little bit about the life cycle of an experiment, which is maybe not so obvious.
Which is maybe very different from the 2 halls that we're seeing.
Right. So,
Okay.
In our field, experiments are big, expensive, and they take a long time. So you want to run an experiment, you think about an idea, then you have to write a proposal, and that proposal is very detailed. It includes a lot of simulations, feasibility studies to prove that your experiment is viable. So you'll probably work with some theorists while you're doing that, run some simulations, and then all of these proposals go to a committee, and that committee ranks those proposals with a letter grade, and either approves them or otherwise tells the people to come back with some more evidence for their experiment. So already this has been probably a couple of years of work, and now you get in the queue to be scheduled, and it could be, a few years, maybe even many years before the experiment actually runs. Then you run your experiment, and it depends on the experiment. Sometimes they're a week long or 2 weeks long, but sometimes they can be years long. And the experiment that Malte and I work on is run for years already. And we just try to get a bigger and bigger data set so that we can look for really, really rare things that don't happen often. And then no matter which way, whether it runs for a long time or a short time, you have to do the data analysis afterwards. And we usually have extremely large data sets, which means that it's quite an involved task with a lot of computing, a lot of work to analyze the data. And that might take some few more years to analyze the data, be really confident in the results, and then write a paper based on those results that you release to the community. So it's, the quickest experiment I could imagine would be 5 years, but, between 10 and 20 is probably more likely.
And also picking up on that large data samples that Mark was mentioning, big necessity and also opportunity for people working in software development or data. Well, I don't want to say exactly data mining, but dealing with large data samples and providing us the tools that we need. So also that is a part of the whole ecosystem.
Yeah, it's important to know a coding language, right? It doesn't hurt.
At least one.
At least one.
Yeah,
That's
I
right.
mean, the experiment that was proposed, that's happening in the hall, was proposed 20 years ago.
Mhm.
It was proposed in 2006 or something. We can imagine 15 years for all the stages that Mark just mentioned, materialize, come to fruition. And then there's a few more years of data analysis, right? So it's a huge penance, I would say. But be thinking about it for multiple years, decades.
Yeah, that's a good point. And something like a particle accelerator doesn't run continuously. So you have certain windows of your timeline when you can actually collect your data. So you might have your project and methodology all set up, but then you have to wait until it actually is up and running, which can delay certain things, right?
that's right. Yeah.
Yeah.
And we try to run 3 or 4 experiments at the same time here at the lab.
Mhm.
They run because we have these separate facilities, A, B, C, and D. They're not necessarily always compatible, so you have to try and schedule very carefully which experiments are running at the same time as which experiments, so that you can provide all the different resources that are needed for the experiments. Sometimes, the electron beam needs to be a very high current for one hole, but it needs to have a very high polarization for another hole, or it might need a very precise energy spread for a particular experiment, these kinds of things. So it's, we work closely with our accelerator colleagues and the lab management to schedule the experiments so that they're compatible with one another.
Yeah. A follow-up question with that is that 5 years sounds like a lot of time compared to other fields. So what future ideas might help reducing that, that you are excited about? So is there a way, I guess, that you can reduce
Right.
that
You
time?
want everything quickly, huh?
That's the
everything
generation, I guess.
quickly.
It's not, it was the question in the chat. The question in the chat.
Right, not you. I mean,
It's a valid question.
Yes, they want to like this.
It's a valid question, yeah. So my take on that would be, while we are running this experiment and while we're taking more data, because we got indication that something interesting is in a certain, let's say, energy range, or somebody came up with a proposal. For example, Mark and I were analyzing data that has been taken a couple of years ago, which went through the entire analysis chain and reconstruction and software, what we were talking about before. What I want to say with this is it's a kind of continuous cycle, and there's interesting data that we collected before, and we're going to use that to make decisions about future data taking. But it's not that you have to wait for 5 years until you can start doing something in general. I mean, there's usually, you get involved in a bigger collaboration of many people. The experiment we are working for has a size of, I would say, roughly 130 people or something like that. And many people have been working on these topics before. And then you can make a proposal for a specific measurement or a specific analysis and work on that. So it's not that you have to sit on the bank and wait for years and years. That's not how it usually goes.
Right. Yeah, you're usually involved in all the parts of the life cycle. You might be proposing something for the future. You might be writing a paper from an experiment that ran a long time ago. You might be currently running a different experiment. So you're involved in many different projects at the same time. I mean, usually if you're a PhD student, you would be specializing in something and just very, very deep in it. But as you get more experienced, you don't really have that luxury anymore, and you have to be doing a lot of things. And
yeah, one of my favorite things of JLab is the international collaboration that occurs inside the facility itself. It's a really cool place to be. So let's talk about safety. There's a safety question here, is how do you deal with safety in the laboratory? And I think, Mark, we saw something attached to your shirt. What is that? Is that what detects radiation? Is that right?
yeah, it's a dosimeter. So
yeah, he's got it too. Mm-hmm.
it measures the dose that you get. But the kind of work that we do, we don't really get a dose. I've never had a measurable dose, but it's still a requirement that I wear it whenever I'm in a radiation area. So in principle, where I am is a radiation area, although in practice, there's very little radiation here.
Mm-hmm. What about other safety concerns that you guys have to take into account?
I mean, I work on the target. As I showed you, the box was closed off, right? It was closed off for the safety reason, meaning that someone who goes in there needs to have all the safety equipment on, and only then they can go in. And they're closely monitored by the safety group that they're actually performing the work according to 80%. So we go through a very rigorous process with safety. Safety are our best friend here. We go through a very rigorous process with safety folks to make sure that we go with a plan with them. We have radiation contamination group, or radiation control group, RADCON. We have many other hall APEX and the work coordinator and the hall leader, and we bring all of them into the same room. I mean, at least for this kind of work that we're currently doing, bring all of them into the same room. We go over the whole entire plan, every detail of the plan, and how we're going to each and every task. And they get a chance to review and give us recommendations on what kind of equipment that we have to wear, called PPE or personal protection equipment that we kind of have to wear. For my project that I'm working on, they have to wear those what do you call those
Hearing protection.
Hearing protection. Then I have to wear laser glasses, and I have to wear a face shield, and I have to wear radiation contamination suit with triple layer gloves, triple layer socks, and I have to change my glove every 1 hour or 2 hours, depending on if there's any contaminated material that I touch. And it's pretty rigorous. It just you have to be. I used to think that maybe we don't need the plan. We just need to come in, take up whatever project is there, and just do it. It doesn't work that way here because people want to see that these documents are well written. We have a plan that is executable. There are no practical difficulties with this approach. So there is a very strict process that any high-risk tasks that are happening at Jump need to be evaluated. So, depends on the task that you're working. But there, you can't just go in and be like, okay, I'm going to do this without any protective equipment. Let's see what happens. Have to be extremely careful.
Yeah. It sounds like it depends on where you are in the lab with the level of safety that's required. Yeah. Another question is, how do you detect anomalies, and what kind of error correction is used in the lab, if any?
Not really sure what's being asked, honestly. I guess they're asking about anomalies being new things, unexpected things, and how do we make sure that it's really there.
Mhm.
Well, yeah. So let's say we're looking for a new particle. So some of the things that we do at Jefferson Lab, it's not our main bread and butter, but we might look for a new particle like an axion-like particle, or a hypothetical dark matter particle, something like that. So we'll take an experiment that was designed for another purpose, and we'll analyze the data to look for this thing. Or sometimes, rarely, we have an experiment that's actually designed to look for a dark matter particle. And then what we do is we do a blinded analysis. So you come up with all your analysis steps before you do the analysis, and everybody agrees on what those analysis steps are going to be. And then you implement the analysis steps, and then only then do you run it through the data, run the data through that, and then see the result. And the reason you do that is because you want to try and avoid any kind of bias that might creep in, and you don't want to analyze the data in such a way that you sort of would make some statistical fluctuation more prominent or something like that, just because you're subconscious bias. So that's what we would do, I guess.
Mhm.
And towards these anomalies, well, I would interpret it the same way as you did, but in general, just as a general well, theme, we're producing these particle collisions, but most of them don't produce anything interesting. That's why we have to produce so many of them, because we're looking for the things that are very rare and that happen only one in a, I don't know, millionth, one in a billionth time. So you need to take a lot of data to get enough evidence for something that is happening very rarely. But at the same time, you also have to record the data. So you can't make it more frequent. Nature does its thing. But we have to make sure to be able to detect these things. And that could be an anomaly in that sense. It's not the uninteresting and very well understood physics that we look at. We look for the things that are not the normal.
Yeah. To better understand. Yeah. All right, let's end on this last question. So how do you have any book recommendations in this area of physics for an undergraduate level?
Undergrad physics level? I mean,
Yeah.
within the curriculum, or?
Maybe
It's
I think they're going nuclear physics.
Yeah, I think they mean nuclear.
That's a good question.
Yeah, Griffiths is a really good book. Introduction to
Great,
Elementary
yeah.
Particles.
Yeah.
Techniques
not so
of
much
nuclear
exactly-
particles.
I was going to say it's not exactly our field, but
Right.
they don't really write undergraduate books in our field so much. So yeah, Griffiths is an excellent choice. Yeah.
Techniques for nuclear and particle physics by Leo, that describes a lot of the detector technology that we're using in the hall. Then, yeah, Halson and Martin, that's for graduate level. Then Brian and Martin, Introduction to Nuclear Physics, is undergrad level. And yeah, I mean, Google also has a lot of references. It's amazing what information you can find. And it's like the challenge of the next generation is not finding books. Challenge of the next generation is focus. I tell you.
Another option is to search these scientists and what they've published for papers and see what they've kind of discovered so far, or anyone at Jefferson Lab. And the particle accelerator is actually across the globe. That would be my recommendation. All right. Did you guys want to add anything else? You have 1 minute.
Yes, come to Jefferson Lab. There's a lot of work that needs to be done.
Yeah.
There you go.
Thank you for attending and your interest in our lab.
Absolutely. So thank you so much to Jefferson Lab for allowing us to see inside of the accelerator. And thank you for everyone for joining us on behalf of the REYES team. And we hope to see you at, I think our next week's our last week of REYES. So see what's available next week to learn about STEM. All right. Thank you again, everyone.
Bye.
Bye-bye.
Bye. Jeff, I think we're good.
Okay, cool. Thank you.
All right, appreciate it. Have a good